Hello, operating systems people. This is Gabriel Palmer, and today we're going to be diving a little bit into operating system design with a case study in the simple parts of capability-based operating systems. And we're going to be focusing a lot on the design of the composite component-based operating system for this. So let's just review kind of what we're doing as operating systems from the absolute highest level. When we talk about operating system design and we talk about providing isolation for the system within a system, we're talking about providing abstractions to principals that are executing on the system. We're talking about sharing hardware between those principals in some methodical and reasonable way, and we're talking about assuring protection between those principals. So if we look at each of these, there are a lot of questions, of course. So which resources should we use to abstract the hardware? What are those abstractions we should provide? And for instance, how can we enable isolation by default, but then controlled sharing when necessary? So as I said, we're going to look at a capability-based operating system design today, and we're going to look at it mainly as a mind game. So we aren't going to look at the details of APIs and whatnot, but I just want to go through kind of the mind game of taking hardware resources and wrapping them in higher level abstractions that leave us with a lot more power for constructing an overall system. I'm not going to go over entirely how the entire system can be made, but just some of those fundamental mind games for getting abstractions and getting primitives. So let's start from the hardware. The hardware gives us multiple cores, which you see depicted down on the left. Each of them has a register set, and each of them has associated with them a timer that can in some way trigger interrupts. We also have dual mode protection hardware, so we have a user level and a kernel level. Kernel level cannot be interfered with from user level, whereas usually user level can be accessed by the kernel. We have ways to switch between the two modes, so system calls where you can intentionally request a switch down to kernel mode, and we have exceptions, which are kind of inadvertent switches usually due to the CPU not necessarily even knowing what to do. Divide by 0, don't know what to do, need to ask the kernel to deal with it. So we have these ways to transition between the modes. And then additionally, we want to interact with I/O. How do we interact with I/O? Well, we have a interrupt controller. This can be a programmable interrupt controller, a PIC, and it will likely have multiple interrupt lines. Here you see one depicted with 5, which means that we can program devices to trigger up to 5 interrupt lines that will execute interrupts within the system. We have a number of devices that are hanging off of the system, and those devices can in some way be hooked up to those interrupt lines. And then, of course, we have a massive and large amount of physical memory in the system. Most modern hardware in some way provides protection facilities beyond just dual mode protection so that we can protect not just the kernel from user level, but also different user level principals from each other. Therefore, we have page tables. So you see kind of the abstract representation of the oval in user level and the concrete representation of the actual page tables in memory in the kernel. And you can see that we're kind of pointing from the specific physical frames that represent the page tables to where they are in kind of this logical sense of a page table. So this is just to emphasize that page tables are actually allocated in memory themselves, of course. Now let's start adding abstractions over what the hardware gives us. So we know that we want to provide protection, and we know that we're going to be providing multiple resources in the system. Therefore, we want some way to track the subset of resources that a given principal will have access to. So the way that we are going to do this is dive into the area of a capability-based operating system, which is to say we're going to add capability tables to our list of abstractions. Capability tables are very simply just tables that are indexed by integers, and each of those integers is called a capability, and the entry that a capability references will either hold a reference to a resource as being referred to by a system call or won't include a resource. Therefore, we probably want to trigger some sort of a exception. So, long story short, some sort of a principal at user level can use system calls to access capabilities and access the resources tracked by their capability tables. This pair of page table and capability table we call a resource table. So we just think of resource tables as being, one of these two types. That's all. And again, I want to emphasize that all of these are just tables that are somewhere in physical memory. The system in many cases is designed to have each of these be the size of a page. Now, if we want to access resources that are memory within a process, then we will essentially be indexing using some address that we're doing a load or store to within the page table to retrieve a frame and an offset into that frame. So this is how loads and stores resolve, right? They go through the page table. So in a sense, the page tables are part of a capability-based system, and that each of the addresses is a capability that is looked up in our resource table to see what concrete resource that actually should be accessing. So this is how we actually look at page tables within a system like this. On the other hand, if we want to execute some sort of more abstract resource within the system, we pass in a capability to a system call that essentially looks up that capability in the capability table and finds the resource referenced at that index, and we'll do some sort of a corresponding operation on it. So this is how we actually access and use the resources that we're given access to in all of our resource tables. And in Composite, we simply say that a component, the orange dot here, that a component is simply a collection of one of these page tables and one of these capability tables. So a component is a notion of effectively a protection domain. Protection domain is effectively the set of all resources that we have access to in the system. This is a single namespace that is easy to implement, fast to implement within the kernel, and it simply, again, tracks the set of all those resources we have access to. So when we talk about components in Composite, we're really just talking about the protection domain, therefore all of the resources that are accessible. Okay, so let's move on. What additional abstractions do we have in the system? Well, it should be no surprise to anyone that we have threads. And threads, of course, take up memory in the system, as with most of these resources. And we're going to depict the logical notion of a thread, of course, as a squiggly line, as one does with threads. And we're going to denote the thread resource in the kernel with the box on the right. And you can see that it has registers that mimic the CPU registers stored within it. So this is the main point of a thread, effectively to be a logical flow of execution, tracking the registers as they change given the execution throughout the component. Notice that threads execute in components. Therefore, a thread, while executing in a component, should have access to all of the resources defined by the resource tables for that component. So now we can start to think, okay, we have execution, and we have the set of resources that execution can use. And depending on how we construct these resource tables, we can make it so that one component is isolated from another if they have no shared resources in any of either of their resource tables. Okay, cool. Now, of course, we don't just have one thread in the system. We might have multiple threads in the system. We may be executing the one on the right, which is why it's more boldface. But we may have references or capabilities in the right component to the threads on the left that are executing in the other component. So this is interesting. You can actually have capabilities to threads, even though those threads might be executing in another component. And of course, you see the logical instantiation of those threads in the oval up top. So, okay. What does this mean? What can we actually do with this? If we make a system call to activate a capability, and we provide a capability that references one of those threads, in Composite, this is actually seen as the command or the request to switch to that thread. So this is actually attempting to do a context switch from the thread that we're executing in on the right to, in this case, the middle thread on the left. So that will actually cause a context switch over to that middle thread. So this is really cool. We now not only have access to resources within our capability tables, but if we have access to a thread, we can switch to that thread. Now we can start actually saying that we're defining schedulers at user level. Indeed, the composite kernel doesn't actually have a scheduler within the kernel at all. All the scheduling policy is defined at user level. So what this effectively means is that our notion of threads abstracts CPUs, right? We no longer need to think of those register sets associated with a CPU. Instead, we just think of threads. And we can start building up the facilities for concurrency within the system using these context switches provided by capability activations of thread resources. Okay, let's move on. Let's continue making the system more and more powerful. Of course, one of the most important things that we need in systems is to provide some useful form of asking another protection domain that might have different resources that it has access to perform some operation for us. So for instance, asking a file system to do a file operation, asking a network server to send a packet out onto the network. So how do we do this? How do we actually create this communication and coordination between these separate components? Well, very simply, we create a synchronous invocation call gate resource within the kernel. And if you have a capability that references one of these as the component on the left does, then you can actually make a system call specifying that capability and activate the synchronous invocation call gate. Every call gate references another component, and not shown here, specifies an entry instruction pointer to actually start executing into that component that will be executed. So in this case, the component on the left, the thread is asking to execute some sort of a function in the component on the right as specified by that synchronous invocation call gate. So when the kernel finds this call gate, what it will do is trigger an up call into the component on the right. And as you can see here, something weird has happened. The exact same thread, the exact same schedulable thread, continues execution in the component on the right. Of course, we're using different execution stacks and all that stuff, so there's safety and there's isolation, memory isolation, but the same thread is effectively continuing execution on the right. This is why we call this a call gate. It's a call gate because a call gate is just a fancy way to say essentially a function call, but with a different mechanism in between. In this case, we're doing IPC in some sense between two components, between two page tables, which is why we call it a call gate. And when we're done executing in the component on the right, because for instance, maybe it's a scheduler and we asked it to block us, and it later wakes us up and we want to return back to the component on the left, all that we need to do is make another system call that returns from the invocation, the synchronous invocation, and upcalls back into the component on the left and resumes the execution where it was executing when it made the invocation. So you can see this looks a lot like a function call. The logic on the left calls a function on the right. It just so happens that it goes between two protection domains and therefore provides isolation. Indeed, this is very powerful. We use it not just for system calls to implement kind of these function invocations between components, but also for exceptions. When an operation happens in the left component, for instance, it accesses memory that does not exist, it will trigger an exception in the CPU that the kernel will use to look up a certain synchronous call gate that will then call into the component on the right that can then actually handle the exception for us. So the kernel no longer really handles many system calls. All of the heavy-duty abstractions for system calls are implemented in other components. Comparably, it doesn't actually implement exception handlers in any significant way. Instead, it just redirects the exceptions to a call gate that's again handled in another component. So, what are we doing? We essentially take synchronous invocation call gates as the abstraction to abstract away both system calls and exceptions, and instead allow both of those to be dealt with at user level in other components. So this is starting to look like a component-based system where we're enabling the invocation of specific functions in interfaces. And those should be very key terms for you by now in this class and should make you realize what we're doing is providing the facilities for abstraction, the separation of mechanism and policy, and modularity. Since these are the foundations of what we want in systems, we're doing this at a very core level with the system abstractions. Okay, let's simplify a little bit and go back to the question of the interrupt controller, the programmable interrupt controller. What do we do with that? What's happening here? Okay, how do we abstract that? We want interrupts in the system, but nothing that we've talked about yet really gets us interrupts. So what we do in the system is we allow very privileged components to have in their resource tables a virtual interrupt controller. This is virtual because it really just is a set of bits saying which of the interrupt lines we're able to actually program. And for instance, here, the non-dimmed out interrupt line is the second one. So we know that we can program that second line. And what do we program it to? Well, we need another kernel resource. So we're going to add in what's called an asynchronous activation endpoint. And in this case, again, of course, it's a kernel resource, so it's referenced from some sort of a capability table. And every asynchronous activation endpoint references a thread. And what we can do with a virtual interrupt controller, when we have access to program a certain line, we can hook that up to a specific asynchronous activation endpoint. And what that means is effectively when the interrupt fires, it will activate the thread associated with that asynchronous activation endpoint. So in a way that I'm not going to talk about here, it kind of has to do with PCI programming and whatnot, one of our devices can be hooked up to a specific line in the interrupt controller. And when that device triggers an interrupt in that line, the kernel will start executing at the ISR, the interrupt service routine, and the first thing that the ISR will do is it will find the asynchronous activation endpoint that it's associated with, find the thread that that is associated with, and then simply try to activate the thread. So what we're doing here is something very simple, but very powerful. We're taking the chaos of interrupts and the idea that they kind of preempt whatever's executing and execute on the stack of the currently executing thread, and instead turn all of that complexity into simple thread activation. So, we're providing the foundation now for concurrency. We can switch between threads by doing context switches in schedulers between threads, and now we have true concurrency by allowing interrupts to activate threads asynchronously in response to that actual interrupt. So we call these interrupt threads, the threads that are activating in response to an interrupt, just as a notational simplicity. And they are effectively a relatively easy to use abstraction of interrupts. Okay, so that's actually only half the story, because that's how you activate a thread in response to an interrupt. But how do we actually allow a thread that was woken up, an interrupt thread that was woken up for an interrupt, after it's done doing its processing for the device, how do we allow it to block? How do we allow it to stop executing? Well, it actually has the ability, because the asynchronous endpoint is in its capability table. It can call down, make a system call, specify the capability to the asynchronous activation endpoint and say, you know what, suspend me please. I'm done executing. I don't want to execute anymore. But we're kind of at a dead end right now, right? Like, what do we do then? Okay, this thread doesn't want to run. But like the normal kernel answer to that would be, okay, call the scheduler, allow the scheduler to decide who wants to run. But there's no scheduler in the kernel. The scheduler, as we've kind of already established, is that component on the right because it has capabilities to all of the threads in the system, right? It can switch between them. Okay, so what do we do now? Well, we need to make this asynchronous activation endpoint slightly more complicated to be able to enable what we want here. So every asynchronous activation endpoint actually includes a parent pointer. So it has a pointer to another asynchronous activation endpoint that we call its parent. And that references a thread, which is actually a scheduler thread. So a scheduler thread is a special type of an interrupt thread that effectively gets notifications of the suspension of, and activation actually, of these interrupt threads. So when the thread on the left says, hey, suspend me please, and specifies the capability to its asynchronous activation endpoint, what the kernel does at that point is it follows its parent pointer, finds the parent asynchronous activation endpoint, finds the thread associated with that, and switches to it. That thread is assumed to be some form of a scheduler thread that is then able to understand that that thread has blocked. It says, oh, okay, thanks for the notification, kernel. I now understand that that thread is done executing, therefore I'm going to block it. Now, the kernel itself actually has no blocking system calls. It has no notion of blocking or effectively waking up. All that it understands is being able to activate threads, switch between threads. So this notion of blocking, the scheduler on the right, when it says that I'm going to block that thread, what that really means is that it is going to just track the state of that thread in its own data structures. And because this component on the right is a scheduler, it will also be doing things like implementing a run queue of all of the active threads. So when the thread on the right, on the left blocks, great, we're moving it from the run queue, putting it onto some sort of a block queue and waiting it for it to activate at some point in the future. And after we do that, we simply want to say, okay, who should I run next? So we consult our run queue, find a thread to run, and then we know how to run a thread. We simply specify the capability that we have to that thread resource that we want to run. In this case, kind of that first thread over on the left, and that will actually switch to the thread. So this is what a scheduler does. You don't need a scheduler in the kernel so long as you have these nice activations that go to the scheduler thread, and you have these synchronous call gates that allow different components to make requests of the scheduler, right? But that's not the entire story, because the scheduler actually does one more thing. When it initially says that it wants to switch to another thread, it wants to context switch to a thread and activate it, start running it, it actually also specifies that, yes, I want to switch to that thread, activate this capability, which happens to point to that thread on the left, but I also only want that thread to run for a maximum of n cycles. So it actually can specify effectively a timeout. After this amount of time has elapsed, then I want to stop executing that thread and receive a notification that a timeout has triggered, that we have run that thread for the specified amount of time. So as you can see here, this actually goes down to the timer associated with the core that the thread is executing on and programs the timer to set off a timer n cycles into the future so that if the thread goes into an infinite loop, we will be able to stop it, run another thread, and then perhaps come back to it later. So this allows us to implement preemptive scheduling. We can implement things like round robin, etc., by being able to program these timers. So schedulers are really powerful. They're able to keep track of cycle accurate time, they're able to interleave between threads, and they're able to interact with these notifications that basically tell us whether interrupts happened or not. So after we program the timer here, that's when we actually, after we program the timer, then we look up the thread and switch to it, right? So this is really powerful. This notion of kind of scheduling with timeouts preemptively is enabled by effectively allowing kind of these scheduler threads to be able to program the timer. So now we don't really think of registers associated with cores, instead we think of threads. We don't really think of timers associated with cores, we think of these scheduler threads maintaining their own notion of time. These scheduler threads have everything that they need to be able to schedule within the system. Okay, this is actually all of the main mechanisms that I want to go through. This is enough to be able to implement concurrency, almost parallelism. We have to talk about how cores can communicate a little bit, but almost parallelism, because all of this can be happening across multiple cores at the same time. We've talked about how to abstract CPUs away with threads, and we've talked about how to abstract protection domains and communication away. What we have not talked about, that I'll talk about in a couple of weeks, is how we manage and allocate memory. There's this notion of typing memory to make sure to use it safely. And we're going to talk about how we manage, create, and abstract resource tables later as well. But for the time being, we will go over APIs to create all these resources, but these are the core resources that are used to construct the entire system. So let's review here. We go from this, where we have dual mode protection, page tables to provide virtual address spaces, exceptions and system calls to switch between different modes. We have an interrupt controller that can be hooked to devices and triggers raw interrupts, horrible interrupts. We have all of our physical memory, and we haven't really talked about how to abstract that. It's fairly direct. We have a register set associated with each CPU, and we have timer interrupts. This is what we have from the raw kernel. And what we've done is abstract it into a relatively small set of resources: page tables, capability tables, components, synchronous invocation call gates, asynchronous activation endpoints, and threads, along with virtual interrupt controllers. And with that, we can effectively have protected execution at user level that can provide abstraction, the separation of mechanism policy, and by design modularity. So we have all of the building blocks with this relatively simple set of kernel resources to be able to build up much more complex systems on top at user level. And this is what we're going to be doing throughout the class. Thank you all very much. See you soon.